This is Larry Benko again, and this video is on matching fundamentals. Before we get started, we might ask ourselves, what is matching and why do we need to do it? Well, matching is converting an impedance at one place in a circuit to another impedance at a different place in the circuit. And why do we need to do it? Well, we need to do it for a whole host of reasons, but generally it's to increase power transfer. If we take a circuit that's as simple as, let's think of this generator here as an antenna, and this load as a receiver, and the receiver is mounted right on top of the antenna. A given antenna will have a certain impedance that if the receiver presents to the antenna, that the antenna will produce the most power into the receiver at that frequency. If that impedance does not turn out to be the impedance that the receiver is, we need to match to the antenna. Or you can think of needing to match the receiver to the antenna's impedance. Either way, it doesn't matter. It's the same circuit. But we do this to increase the maximum power that we can get from one place to another. In the case of a transmitter, such as a 100-watt transmitter you might have in amateur radio, we are given the spec that the transmitter is a 100-watt device. Well, it's a 100-watt device based on some load impedance. And that load impedance that we generally consider that to be is 50 plus J0. However, it may not be exactly 50 plus J0. It probably is quite close to 50 plus J0. In general, if we do things like change the load impedance, let me make a couple little changes here real quickly. Set these things to be linear values just for reasons of convenience. They're 5 ohm steps. If we look at the output power right here, this generator type right now is declared to produce 1 watt into an impedance of Z0, which is 50 ohms. At 50 plus J0, we see 1 watt here. It's probably easier if we change the generator to be, excuse me, 100-watt generator for ease of comparison to the numbers. So we'll start with a 100-watt generator here. At 50 plus J0, we see 100 watts. As we raise the impedance, we see the power drop below 100. As the impedance gets below, or the resistance gets below 50, the power drops again. As the reactance goes above 0, the power drops. As the reactance goes below 0, the power drops. So there's a sweet spot at 50 plus J0 where the transmitter produces the most power to the load. And this is assuming the load's tied right directly onto the transmitter. Any losses that would be in between the two would obviously have to be considered also. But for right now, we're going to tie the load right next to the transmitter. This generator type, UZ0, is exactly how a signal generator works. It's how an antenna works. It's how most transmitters work too, but there are many cases where transmitters don't quite follow that model. But let's go down the road for a while looking at the UZ0 model. If we take and put an SWR curve on the Smith chart here of 2 to 1, and we drag our load impedance to some place on the SWR 2 to 1 circle. Everywhere on this circle is an SWR of 2 to 1. We see 88.7 watts produced at the load there. Let's drag it up here. 89 watts over here. 89 watts over here. 88.9 down here. 89 over here. 89. I think you get the idea that basically no matter where you are on this 2 to 1 SWR circle, this generator will produce 89 watts. This is what's generally in the industry termed as mismatch loss. If we go and look at mismatch loss in Wikipedia, which I mentioned before, but Wikipedia is a wonderful reference on a lot of this stuff in order to enhance your understanding of it. We look at mismatch loss, and it ends up being defined as the percentage of the power you get from the generator that's possible to be produced by the generator to what's actually delivered is 1 minus rho squared. Rho turns out to be the reflection coefficient. The reflection coefficient turns out to be exactly gamma without regards to the phase. So a 2-to-1 SWR, let's see if I can get this right on exactly 2-to-1 SWR here. That's pretty darn close. Here it says that the reflection coefficient is 0.334. Actually, the reflection coefficient for 2-to-1 SWR is 0.3333. So if we go back and look at the Wikipedia formula again, it would be 1 minus 0.3333 squared. Well, 0.333 is 1/3. So 1/3 squared is 1/9. 1 minus 1/9 is 8/9. 8/9 times 100 watts in our example is 88.88 watts. Now, SimSmith shows some slightly different values here, and it's because if you look closely, I didn't quite get that impedance right there. If I get it right on the nose, it's 88.86 watts. If I get it even closer, yeah, you can see I'm not quite exactly on there. But fundamentally, everywhere on this circle, that transmitter produces 88.86 watts. Likewise, if we go up here to a 3-to-1 circle, and again, do the same stuff, drag our load impedance over to here, we see 75 watts, we see 75 watts basically, 74.8, 74 point, I was off a little bit there, but 74.95. Again, back to Wikipedia, the reflection coefficient on a 2-to-1 SWR, or sorry, 3-to-1 SWR is 0.5. So this would be 1 minus 0.5 squared. 0.5 squared is 0.25. 1 minus 0.25 is 0.75. 0.75 times 100 watts is 75 watts. And the power continues to drop linearly in all directions down to 0 at the outside edge. This is exactly how the UZ0 generator works. If we look at it a little more closely, what we see, to look at it a little more closely, let's look at it as a 50-watt generator. Strictly for the number reasons. At a 50-watt generator with a 50 ohm load, the generator produces 50 volts and 1 amp. V times I, since it's in phase because it's a resistor, is 50 watts. That's pretty simple. Now, let's take this 50 volt source we've got here, and let's raise this impedance up to be basically infinity. We're going to raise it up to a megohm. At 1 megohm, we see that the voltage source here is 100 volts with virtually no current flowing. And if we drop it down to 0, we see it's virtually no voltage with a 2 amp current source. So what fundamentally we have here in this generator is for a 50 watt source is a 100 volt generator in series with a 50 ohm resistor. Then when we put 50 more ohms over here, we get our 50 watts. That means we burn 50 watts in this resistor. In the case of a signal generator, we don't really care about that for the very simple reason that the powers we produce out of a signal generator are low. In the case of a transmitter or an amplifier, things are a little bit different. We don't actually put a resistor in there. What we're dealing with is something completely different. We're dealing with a maximum voltage we can produce and a maximum current we can produce. So let's suppose someone comes along and they say to you, I've got a transmitter. My transmitter is a fixed voltage source. And it's 50 watts. So at 50 ohm load, I get 50 watts out again. Everything seems fine. Now, what happens if I drop my impedance here? I drop it to 45, 40, 35. My power goes up. I raise it above 50, my power drops. Well, that's to be expected because power is equal to V squared over R. So if I drop to 25 ohms here, I have basically 50 volts squared divided by 25, which is 100 watts. So if someone tells you that they have a voltage source for their transmitter, it should be your desire to drive it with an impedance that's lower than what they think it might be spec'd at, because you'll get more power out of it. Well, I can take that to some ridiculous point down here, say, now it's a 250 watt transmitter, and you'll say to me probably, well, my generator can't produce 5 amps. And to that response, I will say, well, it's not a fixed voltage generator then. So maybe it's fixed voltage in a little range, but beyond that range, it clearly is not fixed because it has current limits. Likewise, if I make my generator, and SimSmith comes with a lot of generators, but you can write your own formulas. This generator of magnitude of the impedance turns out to be a current source. This generator produces a current source of 1 amp no matter what impedance I put in there. So watch the 1 amp right there. And as I change things, it still produces 1 amp. In the case of me telling you my generator or my transmitter is a current source, it should be your job to face it with a higher impedance, because as my impedance rises, my power rises. 100 ohms gives me 100 watts. Again, at some point in time, I raise it enough, and I've got to say to you, I give, because my generator can't produce any more voltage. So in reality, you have those limitations, even if you think that the generator is a current or voltage source. In general, it makes the most sense, in my opinion, to use the UZ0 generator for almost all cases. There is one exception to that, which is a very big exception. That's the Xmatch generator. And the Xmatch generator, let's set it to be 100 watts again, is a generator that does not exist in the real world, but it has really, really nice characteristics. And that is, it has a matching network on the output of it, which is perfect. That means that no matter what impedance I put out here, it will still deliver 100 watts. So let's look at this. As I change resistance, it's still 100 watts. As I change reactance, it's still 100 watts. It doesn't make any difference at all. So that generator, you say, well, that's stupid if it really doesn't exist. Well, it is kind of stupid. But if I want to look at the loss in a certain part of the circuit, then in the rest of the circuit I haven't built yet, this mathematical matching network can be the rest of the circuit. And it works very nice. Also, if I turn the order of calculations around backwards, which you need to do when you're looking for some kinds of a certain type of problem, you need to run SimSmith in a backwards direction. You need to have the generator be an Xmatch generator if you want to look at the power that you get in that network with the various component values. So there's some reasons to use this. For this discussion today, it really doesn't matter. And UZ0, in my opinion, is the most common generator. So we'll just use that today, and we'll use it as a 100-watt generator. So let's talk about matching itself. When you start to match something, you might say to yourself, I don't have any idea where I even need to start. Let me get rid of this SWR circle here. I can be anywhere I can have any impedance I want on a Smith chart here at any frequency, and I can say I want to match to that point. And you say I have no idea how to do it. And that's probably a reasonable assumption, because until you get used to this, the Smith chart's kind of cryptic. There are places on the Smith chart that are very nice, and let's look at some of those. If we assume that a match from one impedance, well, it won't be 50 anymore, or it won't be 0, but if we assume that let's assume we're up here. I moved the load impedance up there by doing that, by dragging the blue dot, the blue X. If we assume right up here is where we want to start, let's look at what we could possibly have happen here. And I made a few graphics here. Here's a Smith chart that shows 4 individual lines which are very powerful. So if I can get my impedance to be right there somehow, it doesn't matter how I get there yet, but if I can get there, I can get down to 50 in one more step. And the way I get down to 50 in one more step is, it says with a series C. So let's put a series C in there, and we're there. Likewise, if I can get over here, let's say let me drag it over. If I can drag that over to there, I can get here with a shunt C. So let's go up here and I didn't quite get there because I wasn't quite on the line. But you can see that gets there also. Everything on the top half of the Smith chart is inductive. Everything on the bottom half is capacitive. Same two scenarios exist on the bottom side of the Smith chart. So this is one step away from being matched. If you can get anywhere on any of these lines, you're one step away from being matched. So are those the only 4 points on the Smith chart that's true for? And the answer is obviously no, or I wouldn't have asked the question. So let's go and look at these. Everywhere in this circle and everywhere in this circle can be matched with a single component also. That single component happens to be a transmission line of some impedance. The downside to this is that it's tough to buy 97.2 ohm coax or transmission line or 82 ohm or something else. Transmission lines generally only come in a certain number of flavors. There's some specialty people who make coax that's in some low impedance versions that are used for amplifier design, but in general you can't buy all the impedances. However, if you're working at VHF or UHF, you can build any impedance transmission line you want on a circuit board. So while this may not have a lot of practicality in HF, it has a huge value in UHF and high frequencies because of the fact that you can pick a transmission line of pretty much any impedance you want. I mean, very, very low values you can't have, and very, very high values you can't have, but you have quite a range. So let's look at this for a moment. Let's assume I'm somewhere over here, and let's start over here on this side. Let's assume my load impedance is somewhere over here, and I want to match. I'm inside the circle, and I want to match to 50 ohms with a single piece of transmission line. So let's put a piece of transmission line in there. Let's make it lossless just for the moment, because we're trying to show that you can do the function here. And we know the impedance is less than 50, so let's start dragging the impedance down here. Now, while we're doing it, let's increase the length enough so we can see if it ever goes through 50 plus J0 here. And let's continue to drag the impedance down, and we're there. Now what we need to do is shorten its length. So, 18.5 ohm transmission line, that's 15.29 feet long if the velocity factor was 0.6667, would match very nicely. If we had a little loss in the transmission line, it doesn't match exactly the same place, but you can correct for the length a little bit and correct for the impedance of the transmission line a little bit. Let's, well, I don't know, let's, let me pick another point here. How about there? So now we know that the transmission line needs to be higher than 50 ohms. And it's going to be higher than 75, and it's going to be less than 400. So let's change its length. It's pretty close. So 126 ohm transmission line with a length of 11 feet would match. And again, this was done at 7 megahertz. If you pick a new frequency, say like 100 megahertz here, the match still works, but obviously the length of the transmission line varies. It's the same electrical length as it was at 7 megahertz, but that manifests itself as a much shorter actual length. And everyone's probably seen a table that looks like this, which basically tells you all the two-component matching networks and what range they match. If we look at this division of the Smith chart, it's kind of interesting in that it's a circle of diameter, let's just call it diameter D, two small circles that are of diameter D over 2. A D over 2 circle has 1/4 the area of a diameter D circle. So this one is 1/4 the area of the total Smith chart. This one is 1/4 the area of the total Smith chart. Line of symmetry down the middle. This area up here would be a line of would be an area of 1/4 of the Smith chart, and so would this. So each of these 4 equally sized areas have certain characteristics. This low pass L network with the capacitor at the antenna side matches these 2 regions. B matches these 2 regions. C, which is a high pass network, it matches these 2 regions. D matches these 2. Interestingly, there are 4 other matches that aren't used too much. These are used very infrequently, but these are used somewhat for a very good reason. They match up in this section up here, but the two matching elements are extremely low loss. The capacitors are much, much lower loss than inductors. And we can take that into our, we can make that work in our favor for some types of matching networks. Nevertheless, that's probably enough of this. And let's look at a couple examples. If we might, well, let's just leave this where it is here. We were able to achieve a match here on its own with a single piece of transmission line. But if you were given this problem in your backyard, and let's go back to 7 megahertz again. Let's say you wanted to do this at 40 meters, and increase the length of that to where we're there. Basically, what we've got with a piece of transmission line, if it had 0.5 dB loss per 100 feet at 10 megahertz, which is about RG8 type transmission line, we would see that we would have 97 watts of power produced in the load. That's quite a bit. But this isn't the problem that I really want to solve. This problem is kind of an arbitrary problem here, and it gets me 11 feet away from the antenna with my transmitter. I'm going to define a new set of conditions. The new set of conditions are my generator is 50 feet away from my antenna. So no longer is this a useful solution. Well, I shouldn't say it's not useful. We could continue working our way around here again, and we could work our way. There's 50 feet right there. So we're not there at 50 feet. We'd have to go more than 50 feet. We'd have to change our impedance to take into account the loss. We'd have to change the length here again. And since it's more than 50 feet, that's okay, because we can coil it up somewhere. So at 58.5 feet, we get 91.6 watts. So here's a solution that gets us 91.6 watts. However, it's a solution that I would consider to be impractical, because you're going to have a hard time finding this 118 ohm transmission line. So let's basically take this and scrap it and say, what can we do to get from this point to here efficiently? Well, the first case that somebody might do is to put 50 feet of this lossy transmission line in the circuit and then attach to it an L network. If we do that, we're down at 90 watts. And that's not a terribly bad thing. It does match. We lose 10% of our power doing that. We could put the match over here. We see 94 watts. 94 watts is better. Everybody should have heard that you always want to match near where the mismatch occurs. The mismatch occurs between here and the line. Therefore, putting the matching network here is more efficient. This matching network can be low or high pass. We look at the power from either way. It's slightly different, and that's a function of how the current through the inductor primarily. We can do the same thing down here. Goes from 90 watts to 89.9. So that's another way to do it. I would argue this one's probably not very practical. If it's a dipole you've got up in the air or something, you can't hang a match tuner on it. This works fine. It does cause you to lose 10 watts. But for purposes of, and this may be the solution you choose. You may choose to just go and buy a little bit bigger coax and drop this power down a little, drop this loss down a little bit if you wish. But there's a lot of other ways to solve this problem too. So let's look at what we could do here with a different kind of coax. We couldn't get our 100 ohm coax before, but we can probably find 75 ohm coax. Does 75 ohm coax afford us any kind of thing? Does it help us? Well, 75 ohm coax from this point right here does not go through 50 plus J0. But can we make it go through 50 plus J0 with an additional component or two? Would that be something that'd be good? So let's see if we put a component up here. Across the load. Is there any value of inductance that I can put across the load that will make this circle go through 50 plus J0? So let's move it around. And it gets a little bit close, but then it goes away again. So So the answer to that is no. There's no value you can do that with. So let's go up here, Control R, rotate that component. Let's try it again. Whoa, that one goes through. Okay, so that component of magnitude 2.68 microhenries, in addition to some amount of 75 ohm transmission line, would get us there. While we're here, though, let's just do the other two values also. Is there a capacitor that will do this? Not a shunt capacitor. Whoops. There's a series capacitor. Is there any value of the series capacitor that will work? And the answer is no. So the series inductor does work if we get the right value here again. And the right length. Now, if we actually have a piece of 75 ohm transmission line, it'll be lower loss than our 50 ohm piece. So let's say it's 0.4 dB. It'll also have a different velocity factor, probably 0.8 or something like that. And you can put the real values in here. I mean, this is just a guideline as to ways to match. This is set up to be a 60-foot piece of transmission line, and it's too long, obviously. So what we can do is we'll bring it back down here. And we end up here at 7 megahertz with this being 17 feet. I could follow that up with a piece of 50 ohm transmission line to make up the extra 32.62 feet. And our loss would give us 94 watts. So this is more efficient than doing a single piece before where we only had 91 watts. This is 94 watts there at the load. Well, that works out. That's not a bad choice. Another choice is to continue on with our 75 ohm coax and do another rotation. So let's see where our second rotation gets us. Zoom in here a little bit. We got to change our inductor just a little bit because to make up for the loss in the piece of transmission line. We got to change our length just a skosh here. Pretty close. This is 73 feet now, and this is more than we needed. So if we're willing to coil up a chunk of coax somewhere, 23 feet worth of it, we still get 93 watts to our antenna. So this might be considered to be a pretty good choice. We could have done this at some other frequency. Let's say we're doing this at 14 megahertz. Let's assume everything's the same. I don't know this will be a different arc now. 19 feet would be a place you could tap on a 50 ohm coax. 47 feet. This might be quite interesting. 47 feet probably gets you gets you inside the house. And if you really indeed need 50 feet, you just live with 2.251 feet of coax. And this is still 93 watts at 14 megahertz. So these two solutions have a lot of appeal. This inductor that has to go in series with the antenna had to be a waterproof connection already. This is right next door to it, so maybe they go in the same box or whatever you put up there. Then an inductor does not need to be weatherproofed at all. You can wind it out of 1/4 inch or 1/8 inch tubing. You can wind it with 10 gauge wire. It'd be self-supporting. 1.3 microhenries is not. 1.3 microhenries is probably inch and a half diameter, maybe 8 turns, 7 turns. That you can look that up very easily in a book, or there's formulas for that. But everything I've said so far is predicated on a couple things. One was knowing this impedance here. This impedance I randomly just put down when I did this. I could have put it anywhere else on this chart, on the Smith chart, and I would have gotten probably different answers for what the solution was. The solution I get is a function of what I have floating around. If I had no 75 ohm coax at all, that this solution wouldn't be acceptable unless I was willing to go buy some. Fortunately, 75 ohm hardline is pretty easy to come by from cable TV people, and it's probably, and most of it's in pretty good shape, and 49-foot piece is small enough they never use. So those things are available pretty easily. But we're still back to, how did I know what this impedance was to begin with? In order to get SimSmith to accurately do anything, I need to know the actual numbers I've got when I start. It's really, really valuable to have some kind of a little network analyzer to go in conjunction with SimSmith. I use a little AIM 4170 or AIM 4300, 2180. There's other people who make these little network analyzers. If you can get one that can extend the reference plane. When I say extend the reference plane, that means I can take my little network analyzer, it's portable, drag a piece of transmission line out, calibrate it at the end, and connect it temporarily to the end of my antenna, and I can measure this number. If I measure that, SimSmith is capable of reading that number. It can read that number from most of the file formats that are created by little network analyzers. Also, a little network analyzer can be used to measure the inductance that you wind. If you do that, you end up being so incredibly close that if I was doing this, I'd cut this to be 6 inches longer and this to be, I wouldn't even worry about this one, it's so short. Cut this one to be 6 inches longer and maybe trim it down a little bit because this velocity factor might not have been exactly perfect. But it's that close. So you get very, very good results. But you need to start with good data. If you start with bad data, you don't get good results. Another example very quickly would be to take what if somebody said to you, this is a dipole, just bear with me for a second here. This is an easy neck calculation of a dipole that is, hover over here and look up here when I hover there. It says it's a 65.4 foot flat top dipole, made with number 12 wire, 30 feet high. It's intended to resonate in a 40 meter band, and let's see how I did here. Okay, resonates pretty nicely in a 40 meter band. This file that I imported here was the last.z file that EasyNet produces. You can just drag it directly into SimSmith. Now, let's assume for a moment that I'm one of those people who say, I don't need a tuner because I use a resonant antenna. Well, this antenna is resonant, and this SWR here at 7.15 megahertz, I got to get the step size probably right here for what I calculated. There were 25 kilohertz steps, 4 megahertz, 201. If I do that, I should be able to line on that. I don't know. Anyways, nevertheless, this is pretty. SimSmith only snaps on one side of only snaps on where the points are actually located, and I'm not quite there. Anyways, 7.15 megahertz is where it was supposed to be, and those on either side of it. So basically, if I put let's say I've got a transmitter that I declare to be able to put up full power over a 1.7 to 1 or less SWR circle. And that's not too uncommon. That's pretty typical of a lot of HF transceivers. Does this cover the full 40 meter band? Well, SimSmith allows me to put more than one frequency up here in the generator. So let's put 7 and 7.3. We just separate them by space, and now it'll put 2 dots. I clearly cannot cover the full 40 meter band with this antenna. And where do I fail? Well, I fail at 7.24 and 7.04. So I can get 7.04 to 7.24, but I lose 60 kilohertz at the top and 40 kilohertz at the bottom within this and not be within this 1.7 to 1 circle. So here's a case where even though I don't need a tuner, putting a little tuner in the circuit. Now I don't have any transmission line in this circuit, but putting a little tuner in here, setting the tuner to match the center frequency to be a match, we'll put both the 2 points, 7.3 and 7.1. Maybe we should have made that 7.14 was the match point. Probably should have. Okay, that puts both the entire 40 meter band within the 1.7 to 1 SWR circle. So even though you have a resonant antenna, the SWR bandwidth, which is the frequency range where the SWR remains below a certain point, has increased. So there's a use for impedance matching, even though I didn't need it to operate most of the time. Let me see, I can do maybe one more example here. Here's an easy neck calculation. Again, if we look at this line up here again, it is a 20-foot vertical using a mini neck ground. It's 20 feet high. It's center loaded. It's got a 9.25 microhenry inductor in the center, and there is the curve. There's the impedance plot of it, and it's a 40 meter vertical also. It's intended to be used at 7.05 megahertz. And you'd say, well, you were a fool to make it, you should have made it a little bit longer so that 7.05 would be up here at the minimum SWR point. But by making it short, by arbitrarily making it short here, I moved this down. So we did this example before, but this shows the value of being able to sweep this, and there's our match. Now what's our bandwidth? 7.1, 7.0. It covers the CW band. We could have made it cover the single sideband, most of the single sideband band by changing its length, but that's another example of how to do this. Anyways, let's see. Video's getting kind of long, so this has been kind of a off-the-cuff video on how to do impedance matching, and there's a huge amount more that we could do. You could do this. I could pick other impedances. You could change the rules of what's important and what's not important. You can. One thing that's easy to do in SimSmith is I can take one of these calculations and I can just bring up another instance of SimSmith, which looks to be the same as the last one, but it's just a copy of it. And I can go ahead and do another match in this one. When I'm all done, I can compare all the powers. There's a lot of flexibility here, and you're capable of trying an awful lot of things. Again, there'll be more videos, but I hope this one has been interesting, and thanks everybody for watching, and appreciate it.